and the idea of phase changes and how they're the result of energy transfer. So when energy is transferred into our sample or it's forced to leave our sample, the energy transfer affects the particles in two ways. So number one, it changes the average kinetic energy of every particle. Either all of the particles start to move more or they start to move less. And because of that type of change, it also affects the attraction strength between the particles. So I'm going to write attraction strength. So let's just start back at basic ideas. So naming the phase changes. When a solid changes into a gas, our most common term for this would be to melt. But once in a while in chemistry, a slightly older term that shows up is the term fusion. Now, when a liquid is changing to a gas, tying it to that temperature, like boiling point, we say the sample boils. Another term would be is that the liquid vaporizes and becomes a vapor. Now, there is a phase change when you start off as a solid and it turns directly into a gas, totally skipping the liquid phase. So when a solid turns directly into a gas, we say that the solid sublimes. That should be an I there. So it sublimes or goes through sublimation. In the opposite direction, when a gas reforms as a liquid, we say it condenses. When a liquid returns to the solid state, the most common term would be that the liquid freezes. But a couple of other terms that pop up once in a while would be solidify or crystallize. So when crystals form. And then there's the opposite process when you start off as a gas and it turns directly into a solid, completely skipping the liquid phase. So it's the opposite of when a solid sublimes, a gas will depose. Or it goes through deposition. Now the other thing that I like to do is I like to have particle diagrams. So to draw a solid, I draw my particles where they're touching and they maintain as much order as possible. Where gas is the complete opposite, where the particles, they're not touching and there's no order. They're just moving away from each other. And of course, liquid being the middle phase connector, our particles, they're still touching, but they lack any organization. And that just kind of can help us picture when we draw the particle diagrams, when a sample melts or it freezes, the pictures give us an idea of what's happening to the kinetic nature of the particles and their attractions for each other. Now, before I move on to that, okay, I want to just add in here. So it's cyclic. Solid changes to liquid, liquid returns to the solid phase. It is a cyclic process because that melting point value is exactly the same as the freezing point value. And when we hold that temperature constant, whatever that melting or freezing point value is, when we hold the sample at that temperature, the solid particles melt to become liquid, the liquid particles freeze to re-enter the solid state. So that cyclic process will continue as long as the temperature is held constant. And I want to write down a similar idea when our sample cycles from liquid to gas, gas back to liquid, liquid to gas back to liquid. And that's because the boiling point value is the same or equal to the condensing point value. And as long as we maintain that temperature value and hold it constant, we will get a cycling of liquid to gas, gas to liquid, liquid to gas, gas to liquid. Tying in these ideas. So when our sample, so if we're looking at it in this direction, solid to liquid to gas, heading in this direction, okay? This is, as we head into this direction, taking a look at the particle diagrams, okay? Touching order. Touching, no real order. No touching, no order, complete freedom. So to go the average kinetic energy as a sample changes from solid to liquid to gas, we see an increase in that average kinetic energy. We see that the particles, they gain more freedom in their movement, which means we have an increase in the movement or ability to move. Why does that happen? Touching order. Touching, no order. No touching, no order. Well, what's happened to the strength of the attractions? As a result, we see that there is a decrease in the attractions between the molecules. So they're not being they're not being required or being held in fixed positions. So what kind of energy will drive this result? Well, when heat energy enters our solid, the particles start to move more, and then they also have more stored energy, so they're able to push apart. And then when more energy enters that liquid, the particles start to move even faster, and then more stored energy pushes them apart, and their attractions decrease. So this all happens when energy, I'm going to put E for energy, it enters our sample. And when energy enters our sample, we refer to that as an endothermic process. So down underneath, if we move in the opposite direction, where we start off as a gas and we head back towards the solid state, okay, we start to see that the particles have a lot of movement, less freedom of movement, very, very limited movement, so they're held in order. And so we see a decrease in the average kinetic energy. So we see a decrease in their ability to move. But we go from no touching to, hey, they are touching, to, hey, not only are they touching, but being held in a very specific order or fixed positions. It's because we see an increase in the attractions between the molecules. This type of result, less movement, greater attractions forming the solid, this results when energy leaves our sample, which we would say if energy is exiting our sample, that the sample is going through an exothermic process.